Okay, time to start. So thank you everybody for being here. Our speaker today is Ulisses Almeida from CBPF. As usual, I'm going to introduce a bit our speakers. So Ulisses got his PhD in 2011 in the University of Durham in UK. And before joining CBPF, he has been an assistant professor at the Max Planck Institute in Munich. And in 2014, he has been elected fellow at the Institute for Advanced Study in the University of Durham. He also got an important prize called Jovem Astronomo from the Brazilian Society of Astronomy in 2017. And he also got a grant from the Serapilera in 2019. Let me also emphasize that he's a bit Italian by adoption, since he has two visitor positions in Italy, one in La Sapienza and the other is in the University of Padova from Italy, and I can certify that his Italian is way better than my Portuguese, which doesn't mean much, probably. And the talk of today is going to be about the status of the Southern Wide Field Gamma Ray Observatory project. Ulisse, the floor is yours.
Thank you very much. Dario, can you hear me well? Yes, good. And is this machine following me? No. Oh, now, at some point it will, I guess. Maybe I should show myself. We are presented, yes. So it's a great pleasure to give this talk to you here in the context of this school. And to see so many of you, so many students attending the school, it's very gratifying. And also to take the opportunity to thank Nathan, to thank Rogério, and all the people of ICTP that, of course, are making this school possible. I'm going to talk to you today about a project. It's a very experimental, rather instrumental, and perhaps even managerial at some points talk on the status of this gamma ray project that, in which Brazil has a very important position. But also, South America as a whole has a very important position, which is the project to build the future ground-based gamma ray observatory, extensive Earth shower array gamma ray observatory in South America. So I'm going to talk to you very briefly about gamma ray astronomy. What is this field? What we do in it? And where SWJO is inserted in this field. Of course, you are having a full week. Most of you are having a full week of school in this, so this will help, I guess, to get into what I'm going to say, although I'm not going to delve into details. I will spend most of the time talking about the R&D phase of SWJO, which I think is the really interesting thing that we have to show at this point of the project, that we have just concluded the instrumental development, all the steps to refining this new instrumentation, to define its characteristics, before we start, or actually we are already starting the grant applications to get the funds to build it. Of course, in any astronomical experiment, the cherry on the cake is the selection of the site. It's also the thing that breaks all symmetries and collapse all wave functions, so everything becomes clear after that is the moment of truth. We have gone through that last year, and this is really what took us out of the R&D and into the preparatory phase to build the instrument. And I'm going to give you some perspective about next steps, which is what we plan to do towards the end of this year and next year with the project. So, as you have been hearing, gamma ray astronomy is a very broad field. It started with satellites, but then it's moved to ground-based to reach the highest energies, and this is what we are going to concentrate on today. So when you talk about ground-based gamma ray astronomy, we are talking about TeV to PeV gamma rays. This is a range of energy that's very interesting, not only because it's very broad, so you can cover a lot of phenomena in this very extensive energy range, but also because this is the energy range that dialogues directly with many multi-messenger signals, like cosmic rays at the knee of the cosmic ray spectrum, as you have seen, and the neutrinos that have been observed from extraterrestrial sources by instruments like IceCube, about which you also heard in this school. So one could say that ground-based gamma ray astronomy at these energies is the cornerstone of a new area of astrophysics, phenomenological more than anything else, which is the multi-messenger astrophysics. So it really allows you to bring this multi-messenger signals, cosmic rays, gravitational waves, neutrinos, that are a bit elusive in the sense that it's difficult to pinpoint their origin, and connect them to the astrophysical sources or the probable astrophysical sources that should be producing them, and helping us, through the detailed modeling, understand what are the physical processes that are driving the production of these important signals, which then, for example, in the case of neutrinos, can disentangle the sites where hadronic acceleration is happening or hadronic interactions of high energy are happening in the astrophysical sources, so that we start to understand the physics of cosmic rays better. So there is a plethora of topics that are covered in this. One that is very interesting to mention is the fact that because we are dealing with these very high energies, we can probe some phenomena that are not only, let's say, standard astrophysics. So we can probe phenomena of a new physics, new fundamental physics, beyond standard model physics in space, and probe, look for signals of things like dark matter annihilation and things like this. So it's a field which also then interacts a lot with particle physics, and that's why it really sits very well in what we call the astroparticle physics scenario. Currently, the field is defined by a few experiments that have really transformed the scene over the, say, last 20 years. When I started my PhD, so 15 years ago, the field was really taking its first steps. So no, I finished my PhD 15 years ago. When I started almost 20 years ago, the field was really starting to get into the mainstream with what we call the third generation of imaging atmospheric Cherenkov telescopes, which were these instruments that you see here, Veritas, MAGIC, and HESS, which took this field from an experimental, instrumental field where you had a few sources and you were dealing with the detection techniques more than anything else, to a field where now in astronomy we have hundreds of sources and we can actually do astrophysics with it. So these experiments now are reaching the end of their lives after 2 decades of operation, and they're going to be superseded by something much larger. In parallel, and with some delay, another field was coming up, or another technique was coming up, which is what we call the extensive air shower arrays. So instead of observing I'm going to explain this a little bit better later, instead of observing the Cherenkov light from the extensive air showers, we use directly particle detectors to see the secondary particles of the shower. These detectors have as characteristics the fact that they have to be in high altitude, so that you can be in the middle of the air shower as it develops, and it has to be very extensive to collect as most particles as possible of this very distributed phenomena, which are the air showers, the atmospheric air showers. And for a long time, Tibet was driving the field in the northern hemisphere. It's very close to Lhasa in the Tibetan plateau. And Hawk in the US was obtaining the first, most strongest results. It's an American-Mexican experiment in Mexico. The next step for the field, part of it is already happening, which is the LASSO, a very large kilometer-square array in China, also at very high altitude in Tibet, but with an extension and observation power much larger than the one of Tibet. And it has been very revolutionary, as I'm going to show. And of course, the imaging atmospheric Cherenkov telescopes, all the community has united behind a large project called the Cherenkov Telescope Array Observatory, of which Brazil is a consortium member, so has invested a lot in the last 15 years in the development of the science and preparation for CTA, and now is at the edge of becoming a member of this large international experiment. And of course, when it comes online, it's going to have 2 sites in the north and in the southern hemisphere, in the Canary Islands and in Chile. And when it comes online, the others are going to be shut down. And then there is SWJO, which is the topic of this talk. So I think you have seen it, or at least those who are following the school have seen this. The difference between these two techniques, I mean, both are looking into gamma rays from the range of the TVs to the PVs, but they are actually extremely complementary. So the community understands that you have to operate both kinds of instruments in both hemispheres to take the most of the field. So the difference basically is the fact that with these atmospheric Cherenkov telescopes, you are observing the Cherenkov light emitted by the shower, which has a series of consequences. The first consequence, let's start with the positive one, is that you are following the development of the shower in the atmosphere. So you have a very good calorimetry of the shower. So you use the atmosphere as a calorimetric detector, and you can have a very good reconstruction of the energy and the properties of this shower so that you can reconstruct the characteristics of the primary particle. So you make a movie of the development of the shower with this technique. The problem is the Cherenkov light is very dim, so you can only operate in nights where you have no moon, which means that you have more or less 1,000, 1,400 hours, something like this per year of available observation time if you always have clear skies. If you consider that it takes at least 50 hours to observe a strong source in the field, then you do the maths, and well, the sky is very big, there are many sources, it takes a long time to go around and observe sources in detail. So this is a pointing instrument, and you really have to know your targets before you go into the observation. But of course, as I said, it's a precision instrument. The air shower arrays, they are always less precise, and they will always have larger uncertainties because you are not making a movie of the development of the shower, you are taking a picture of the shower when it passes through your detector. So you only have a snapshot of the whole history of the shower, and you have to reconstruct the characteristics of the primary particle with this picture. So all the fluctuations implicate much more your capability of reconstructing what you're observing, the primary particle characteristics. But it has two advantages. The first advantage is that it's wide field. So you can observe a 1.5 steradian typically at any given time. So if there are transient events that you can detect, that's perfect because you can see many of them serendipitously without having to point to them or to anticipate their occurrence. And the other thing is that even if you are operating at much higher energies, and this is actually the reason why we can operate in much higher energies, and the sources are dim, you are integrating them every day, 365 days a year. So even a very weak source, if you have a good background separation, you are always integrating the signal. So over years, you actually can build a very good map of the sky. No? And this is why you can go to the PVs with these kinds of instruments. And you cannot do that easily with Cherenkov telescopes because of the integration time. I mean, the Crab Nebula, in a square kilometer detector, you can see from it, the Crab Nebula is the strongest source we have in the field. At PVs, you can see 2 photons per semester, something like this. So it's, you have to wait time to integrate. But these guys can do that. So they're very complementary. And the history of these extensive air shower arrays has been a history of trying to go to the extreme of the geographical and experimental characteristics that you need to excel in the field. So the first of them is a collection area, which went from the first experiments from something like 6,000 square meters up to 1.2 square kilometers now, which is what we have with LASSO. And this is simply to allow you to have a good collection of the low fluxes of the sources. And the other thing is to go higher in altitude. So nowadays, all these experiments are around or above 4.5 kilometers in altitude, so that you can really be in the middle of the air shower when it develops. So you have the most quantity of particles, and so you can have the best snapshot of the physics, of the development characteristics of the shower when you observe it. So as all of these fields that are technically, experimentally very challenging, the development was slow and modest. So in the beginning of the century, Milagro, which was the precursor of all these, has been able to detect a few sources, but over almost a decade of operations, you only had a handful of them. The brightest ones could be detected. But very quickly, when Hawk came online, the number of sources increased to a few tens, and this was already enough to establish the field as a new astronomy field in itself. And today, we are in a situation that is very amazing when you think how fast it developed. So LASSO, with its first catalog, which was done only with 2 years of observations, was able to detect 90 sources. Many of them, which have never been seen in these energies, and very significantly, 43 of them which were detected with 5 sigma, which means firmly detected above 100 TeV. Now, these sources are what we call the pevatrons, and is one of the things that we are looking for in the field. And the relevance of these sources is because sources that can show a persistent flux of gamma rays at these energies or above, they are capable of accelerating particles up to the PeV scale. And this is the knee of the cosmic ray. So it's the region where we believe the highest energy cosmic rays of the galaxy are being accelerated. So in terms of understanding the particle acceleration in the galaxy and cosmic ray physics in the galaxy, this is extremely important because for the first time, we have a map of where this acceleration is being done, or at least where the particles are propagating and interacting to emit the gamma rays that we see. So you can track the highest energy cosmic rays of the galaxy through this. So over these few years, since these experiments are working, there has been a number of results. I'm not going to enter into detail in any of them, but I just want to give you a perspective of what are the kinds of things that we see. So one thing to keep in mind is that always when we are observing at these energies, we are looking at extended sources. Not because the acceleration regions necessarily or the production regions of the cosmic rays are this extended, but because we are seeing the propagation of the high energy particles and their interaction with the environment around. So many of the bright things in gamma rays are not the accelerators themselves, but are actually the molecular clouds, for example, around that are serving as targets for hadronic interactions in astrophysical environments. Or media that have intense magnetic fields, which then also radiate through electromagnetic processes. So we are probing not only the sites of origin of cosmic rays, but the physics of propagation of cosmic rays as well, which is a very interesting thing to understand the effect of these guys in the galaxy and to probe other things of the galaxy as a consequence. We have seen very interesting sources, for example, jets of microquasars that emit very strongly in these energies. Of course, as I said, we have seen pevatrons, so a number of sources where you have PeV particles radiating. Nowadays, we have this is the strongest source that we have, persistent source that we have in the sky, which is the Crab Nebula, is also our calibration source. So you can see here the spectra of the Crab Nebula built over several years and decades, all the way from space-based instruments to the PeV with LASSO. And you can see a very smooth spectra connecting, showing that really the results are very solid and the thing fits very well into a unified picture. This is extremely important because we need this kind of data to model the astrophysics of these sources, the radiative processes that are going on at these sources. So it's amazing to see that now we can see this spectra up to its very end. And of course, this doesn't mean that the source has exhausted its capacity of acceleration here, but we are really getting to the limit that we can hope to observe in astronomy. So we are really completing the observational spectrum of these objects. And then you have very interesting sources like this bubble here, where Cygnus, the Cygnus region, where you have a number of, it's a region of star formation, you have lots of massive stars. These massive stars, they have winds, they explode, and so you have these bubbles, which are ejected materia, over-ejected material at various scales, and 10 PeV photons have been observed from this. So we are starting to see the kinds of environments that are the most efficient particle accelerators, perhaps because in this you are undergoing hierarchical particle acceleration. So you have multiple fronts of shocks where particles are pre-accelerated and re-accelerated in sequence, and we start to be able to model a little bit how this process can happen. So it's it's a very rich field in what you can probe in terms of particle astrophysics. Of course, we have also very interesting events. This is the only gamma ray burst that, and you have heard about that a lot in the first day of the school, is the brightest gamma ray burst ever observed, and of course in these energies as well. LASSO could only observe it. They were extremely lucky because it has a large field of view, and the guy exploded exactly over their field of view. So they could follow all the evolution of the source. And with this, they could detect for the first time the start of the emission, of the extremely high energy emission of these sources, and follow its development over time. The source was so strong that, as I mentioned in the first day when we were discussing, people could see the effect of the ionization of Earth's upper atmosphere from the gamma ray flux of the source. It was extremely bright. And the fact that LASSO detected several tens of thousands of photons in a window of a minute or so from this allowed us to study jet physics in a way that it couldn't be imagined before. So you could study all the evolution, the relativistic evolution of the jet as it was developing through the light curves of this source. And here is just a comparison. The strength of this object, which is the brightest one, both means brightest of all time, compared to the other strongest gamma ray bursts observed. So as you know, gamma ray bursts are extremely interesting astrophysical objects, and we have never had the perspective even close to this of the high energy engine of these objects as we had with this single event. We don't expect to detect gamma ray bursts every day with these kinds of detectors, but this is to show that you don't need to detect many if you detect them so well. No? And this is the power of these kilometer square collection areas. So why do we need, and if we don't do that, someone is going to do that, probably the Chinese. Well, but they can come here, yes. So why do we want to go to the southern hemisphere? The answer is pretty obvious for an astronomer. That's where you can see the galactic center from. So the galactic center is where you have, well, Sagittarius A star, where you have all the environment around the central black hole, where you have the bubbles, Fermi bubbles, and where you have the biggest density of high energy sources, a lot concentration of molecular clouds. So it's a great mess for these kinds of instruments to observe. There is a lot of signal coming from there. So the current instruments that are able to probe the TV and PV or the PV sky are all and have always been in the northern hemisphere. So we are actually opening, I think, what is the last available astronomical window that has never been seen, which is the sky above 100 TV in the southern hemisphere. All the rest has been seen, except the sky above 100 TV in the southern hemisphere. So this is the last window for observation. So it's guaranteed that there's going to be discoveries, or at least new sources, new sky maps, and then that's it. What comes after is just refinement. And you can see here the field of view of SWGO in comparison to the sources of the galactic plane that have been detected by HAWK in red and by HESS, which is the other Cherenkov instrument operating in the south, but at lower energies. And you can see that SWGO will basically pick all the collection of them. Our observation capability, I mean, we don't see the anti-center galactic, the galactic anti-center, which is what the guys in the northern hemisphere see the most, but we see the region around the galactic center, so the inner galactic plane, which is where the really interesting things are. So our collaboration is started in 2019, which is a bad year to start an international collaboration, because 1 year after or 6 months after there was the pandemic, so we couldn't see each other. It took 3 years for me to meet Claudio in person. I remember when the first time we had a meeting of the spokes team of SWGO, I went to Jim Hinton and said, "Oh, you look taller in Zoom," actually, no? Because, I mean, we stayed 3 years working without seeing each other. And of course, for an experiment that's looking for a site to the installation of the instrument, that's even worse, because we had to wait 3 years in preparation. So it delayed us a bit, but we started with 9 countries, and now we are 16. We are around 100 associated institutions, plus a number of supporting scientists. So our scientist count is around 200 plus. So it's a large collaboration. Here is a close-up of the European partners, but I want to call your attention to the fact that the Latin American community of the project is very large. So we have 5 countries that are member. So Brazil, Argentina, Chile, Peru, and Mexico. And all of them have a large contingent of people involved, several institutes, tens of scientists. So this is an experiment that I like to say that has the potential of being, and perhaps could be the first, not only an international experiment in Latin America, but a Latin American experiment, because we have a critical mass of people that could actually help drive the leadership and the developments of the experiment. The project status, just so that you know, I mean, we have, this year, this moment, we finalized the design of the core, and we are concluding the design of the outer array of the observatory. So it took us a bit more than we expected. It took us 6 years to arrive at this point, but we have successfully concluded all the activities that we planned for the R&D. And we are now entering what we call preparatory phase, which is the detailed construction planning and a first pathfinder that we want to install at the site to test how things are. And you would imagine that the things that scare us the most are the behavior of the electronics, the behavior of the detectors, how the software. No. It is the border control, it is the bureaucracy, it is the papers that you have to sign, how you import without paying taxes, or how you do things with the consent of the local communities and no damage to the environment. I mean, we want to test these kinds of things, which is what you need to live in a place for 20 years, as we will. We have recently published, although this is not the focus of my talk, it would merit a talk only for this. It will be an interesting one to give, of the science prospects for SWJO. So this is a 50-page paper that we put out on arXiv. Now we are preparing it for sending to a journal, with all the science that SWJO could do, or at least all the core science, so the driving science cases that drove our design. There is much more that can be done, and we hope the community will then be able to give new ideas, but it's very rich what these observatories can do. And you have seen things from search for axions, to Lorentz invariance violation measurement, to search for dark matter, intergalactic magnetic field, beyond all the astrophysics that you normally do with these kinds of things. So this is just to show, I mean, this is the very first thing that we did at the collaboration. At the time I was the science coordinator, so I coordinated this exercise of getting all the science cases that would be driving the science of SWJO and derive what would be the design implications of these science cases, so that we were sure to have an instrument that answered the pressing questions of the field and was also therefore expected to do new discoveries, so answer questions that we don't have yet. So this is just a very simple exposition of the kinds of things that we were deriving from this. Of course, it had to go into the details of the dimensions and the sizes and the quantities of detectors, how they operate, angular timing resolution, charge resolution of the electronics and things like this. So this is just to show, for example, how would be the synergy between SWJO and CTAO if both observed a gamma ray burst that is exploding in front of you. So SWJO is these orange points that would be able to see the evolution of the light curve from the start, and then CTAO would follow up on the SWJO observation, extending the light curve with much more precision, allowing us to understand the evolution of the source much better. So this is important to show because, of course, these are two experiments that are being built now in the same field. So we have to explain why they are complementary and why it's not a waste of money or a superposition to do two such detectors. No? Another thing that was shown by Michele very clearly yesterday, for example, when you think about WIMP dark matter, of course, looking for gamma signals in the gamma rays is something that the community has been doing for some time now, and that this is the sensitivity of CTAO, and you can see that SWGO, because it can reach much higher energies, it goes beyond what CTAO can do. So even in these kinds of science cases, SWGO is extremely relevant to complement CTAO and other Cherenkov instruments currently active. So these are some of the things that we also show in the paper, the complementarity between these two experiments. So the detector is going to look like this pictorially. It's going to have a core, which needs to be very dense, and it will be surrounded by a very extended sparse outer array. The reason for that is simple, is because at the core, you want to see the showers that are the weakest, so you need to have a very dense coverage to detect more particles and be able to reconstruct these weak showers that have less particles in them. Whereas for the outer array, you want to use that to detect the highest energy showers, the PV showers, and here the problem is the collection area. They have lots of particles in this shower, it's not a problem, you can collect then with sparse detectors and it's sufficient to do the reconstruction, but you need to cover a large area to get several of these photons. So another thing that is important is to be very high in altitude so that you are, at these altitudes, we are in the middle of the shower development of 1 PV shower. So the X max of the 1 PV shower is around 5 kilometers above sea level, so you are in the hot spot, no? And the other important thing is the capability to detect the muons, which are, in terms of shower content, the main separator between a hadronic shower and a leptonic shower. So to identify the muons is the best way that we have to do background separation. And in this field, this is very important, because the background is 10 times higher, or 100,000 times higher, if you are at the PV level, than the signal. So you need to do a very good background separation. And this is what LASSO does with perfection. So here you can see, I always forget to correct this picture. The thing is out, the axis name is out always. So this is the number of muons in the shower, and this is the number of electrons in the shower. So two quantities that you can measure well, as long as you have some way to identify the muons clearly. You see that beyond 10 to the 3 electrons, I don't have by mind what's the conversion in energy, but I think this is around 10 TeV, or a few tens of TeV. The two populations of showers are completely separated. So since LASSO can measure muons with such clarity, they can operate background-free, despite the fact that the background is 100,000 times higher than the signal. They operate background-free above 100 TeV, which for a particle physics experiment is excellent. And so they can suppress all their proton flux and keep only with a very high efficiency the gamma ray flux. And that's why even if there is only 2 photons coming from the crab every semester in the detector, they know that's a photon. So it's not a problem, they just integrate. And so it's an ideal experiment. There are other ways to do this, which is not only counting muon, and I forgot to say how they do that. I mean, that's obvious. As muons are penetrating particles, so what you have to do is you have to shield part of your detector so that you absorb all the electromagnetic component, and then you have only the muon signal. They do that by putting their detectors, several thousands of them, water Cherenkov detectors, under 2 meters of ground, of dirt. Of course, you can guess from that this is not cheap. And we are not in a position to spend too much money nowadays in these kinds of experiments, so we have to innovate. And that's why we look for things that try to explore things like the shower footprint. So this is not the footprint of the shower in particles. It's actually in Cherenkov light, but one traces the other, so it's not a problem. So you can see here that a gamma-initiated shower is simply one shower that you have learned today with the Heitler model from Rafael, developing in a very organized way with only decay processes, and so it's very focused, and you have very little noise around, so you can see a very clear shape. Whereas the proton shower, you have hadronic interactions, you have pion production, so it's much more scattered. And in fact, this pi zero showers. They are the pi-zero particles that they decay in gamma. They are going to produce sub-showers that are going to develop as leptonic showers, and that's why you see then these focuses of concentration of energy in the ground, because you are seeing the sub-showers where the energy is channeled via the pion decay. So they are very different. So if you can explore the footprint of this, you can also do gamma hadron separation, but it's not as clear as the one that is done with the muon counting. What comes to our help is the fact that when we started in 2019, there were no large language models or very complex machine learning tools that now are becoming more and more available, and they are really improving our capability of doing this reconstruction and this gamma hadron separation without recoursing to hard detection of the muons. And this is what we are trying to do. If we can advance, and that's where we are going, a detector that is fully based on ground detectors, an observatory that's fully based on ground detectors, we can build a facility like this for a modest price, something around $60 to $8 million, covering an area of 1 kilometer square, with the same or even better sensitivity than LASO, given the capabilities that we have to reconstruct the signal with new computing power nowadays. So, in real life, things are much more dirty and less glamorous, because what we are going to do, our observatory is going to be based on water Cherenkov detectors. And water Cherenkov detectors are basically water vessels. So we spend a lot of time trying to understand how to build the best tanks in the cheapest way, and in the easiest way to do that at 5 kilometers in altitude, where you cannot labor too much. So these tanks here are the ones that are heritage from Hawk and developed by the American team. They were developed to be easy to mount, even being very large at extreme altitude, where work is not, hard work is not so simple. And these are the tanks that we developed here in Brazil following the experience of Auger. As you know, the Pierre Auger Observatory uses water Cherenkov technique as well. And the tanks that are in Auger, half of them, or almost half of them, were built in Brazil. So we are tapping on this experience to also contribute to SWGO. Of course, there are lots of developments in photosensors, electronics. As you heard, these signals, they last for nanoseconds, so we are talking about very fast electronics, very sensitive, and we have to innovate in certain ways. So, for example, usually these experiments, they use single large photomultiplier tubes, which are expensive, which can take years to be delivered if you need them in large numbers, because they are made by hand, one by one. But nowadays, we have these 3-inch SPMTs that are used in experiments like neutrino experiments, like KM3net or IceCube, and we can, no, sorry, not KM3net, and we can transfer this technology to SWGO with the advantage that, well, with 7 of these PMTs, you have the same collection area as a single large PMT, but you have directionality of the arrival of the Cherenkov light in this module here. So with machine learning, you can start to try to use the asymmetric distribution of light in this sensor to understand where the particles are coming from, where the shower is coming from. And by doing that, you can, for example, trigger based also in this information and reduce noise, which is extremely important if you want to reach low energies, 100 GeV, for example, at high altitudes, where you are going to have more than one shower coming simultaneously to the detector and producing a very noisy signal. So this was impossible to do without the current machine learning tools that now are available to us. And we are starting to see how this asymmetry can be used to reduce noise and also detect, for example, the presence of individual muons in a surface detector, because the muon penetrates more into the tank than the electromagnetic component, and so it also gives an asymmetric light. This is all very sensitive. You're talking about small signals, but with machine learning, you can start to separate the things. So this is very exciting and really means that we can reach our targets. Just want to mention, because when we talk about science nowadays, investment has to have an impact somehow. And in our case, we were very lucky because we went back to the company that built the Auger tanks, and we proposed to them a challenge. I mean, these tanks are going to be 5 kilometers in altitude. Now, this looks very simple. In fact, it's not as complicated as many of the things that we have discussed. But one of the challenges was how to make these tanks thermally insulated so that they wouldn't freeze. And we put this challenge to the company, and it turned out that no rotomolding company in the world could do an insulated rotomolded tank. It's not produced anywhere, and when we talked to the people that conducted the development of Auger, people from Fermilab, they said, it's totally impossible. No, we know about rotomolding technique, you cannot do this. We talked with companies before. So these guys took the challenge, this company here. They invested their money because they understood there was an application in the industry that they could profit from, and they developed a technique which now is unique in the world, is a patent from them, to produce these tanks, which are basically one tank inside the other in the rotomolding process, so that they can put some foam to insulate. Now, this turned out to be a big business for the agro, because many of the inoculants of plantation in the agro are live material. And if you take to the middle of a farm live material at 40 degrees sun, it's going to die after some point, because the temperature is going to rise. And so you have a logistical problem of having to bring the inoculant in farms to storage places, and this is money, this is time. Now you can leave this day and night for as long as the thing lives in the field, and this simplifies logistics. So they're already profiting off this. We didn't build the project yet. We don't have the funds guaranteed for it, but these guys are making profit out of the development, the technology that was transferred via the project to the industry. So this is important things to say, because to participate in a large experiment, if you don't have a clear impact in the industry, it's more and more difficult to get the money, especially when you're talking about millions. Now, these tanks are there since in Chile, which is going to the site, since a few months. So they are waiting to be installed in our Pathfinder. And you can see here some of us. You can see here a guy from the embassy of Brazil in Chile that is helping us in this process of constructing the observatory there with some Brazilian leadership. You can see the owner of this company and the chief engineer, because, I mean, these detectors are very large. So they're not expensive. They're $2,000 to $3,000 each. We need thousands of them, but they're not expensive in itself, these tanks. But they are very large, so that to take one from Brazil to Chile, it costs almost $10,000 in transport. So if you don't produce them at the site or near the site, they are not, it's impossible. So the company went there with us and with the help of the embassy to try to see if, to talk with the Federation of Industries of Atacama, to see the region and understand if they can build a factory there, a joint venture there, some type of business there, so that they can build the tanks for us and maybe internationalize the company in the process. So another thing that adds value to the investment of the public money in science. So these are things that we have to deal with when you build a large experiment. I mean, you cannot avoid, and it is actually a good thing. We have to gain more and more experience in doing these kinds of things. So they developed a model for their business there. The idea is to build the tanks 2 hours from the site. And they have a way to do that. They know how they can start a business there now. And now we are waiting for or looking for the funds in Brazil to start this. So I think I'm going very slowly, but it's okay. So this is going to be a next generation observatory. The main reason is because we are trying to use all the new machine learning technique that's available to us and all the innovations that we can make, from insulation of plastic tanks to new electronics, I mean, in all fronts. We turned every stone in this R&D process to try to do something new and better in every front to make the project cheaper. We don't need to make something better than LASSO, but we need to do LASSO an order of magnitude cheaper. Otherwise, nobody's going to pay for that in the West. So, and this meant that in the simulation side, we have to explore all the phase space, which is something that had never been done in the field as well. So usually people have a good intuition of what they have to build, what are the main parameters. They have decades of experience of previous experiments. So they build over it, and they basically have a design almost from the start. In our case, We didn't have a design from the start, and we didn't have a design for 5 years. We were simulating all possible combinations of array configuration and detector geometry with different electronics and different triggers and different photosensors to see what is better and in terms of cost effectiveness. So our simulations, they had a fixed cost, and within this fixed budget, you just change things in order to see what's the most cost effective. And we learned lots of things. For example, how dense you have to be at the core to do all the science that you need. And we learned that you don't have to have 88% density, which is something that one would assume. But when you go beyond 40 or 50%, you don't gain any more to do your science. So you can simplify your logistics there. The same thing is what is the minimum density of detectors that you need in the outer array in order to be able to reconstruct showers. And then you also understand the limits. If you go below 1%, 1.5%, you are not able anymore to do the reconstruction of the PV showers. And this is because previous experiments haven't detected the pevatrons 20 years ago, because they were just below the 1% threshold. But of course, at that time, it was impossible to do these simulations, right? And then we came up with a design that is optimal in terms of cost and performance. So here you can see our capability for the moment for gamma hadron separation. We are not there yet in terms of gamma hadron separation as LASSO is, which is around 10 to the 4, 10 to the 5, the rejection of the background. But we are approaching it with better computing techniques. We are going to have to rely completely in computing techniques because we are not going to have a clear muon signal. We always have to see parameters in the showers that are proxies for the presence of muons. So this is a challenge, but machine learning is helping. Nevertheless, we are adopting at the core of the observatory, and this is still an open question for the outer array, a double layer solution where you have a large quantity of water in the top so that you stop the electromagnetic signal, and then mostly muons cross. Of course, when you have very energetic showers, you have punch-through of electrons anyway, so it's not a clean muon signal as you have 2 meters below the ground, but it's good enough to help you improve the sensitivity of gamma hadron separation the way you need. And in these small tanks that we want to put in the outer array, we are exploring these multi-PMT modules to see the asymmetries and with machine learning to resolve the presence of muons. So here is the expected sensitivity of SWGO, and you are going to see that it's pretty impressive. So this is Hawk sensitivity after 1 year of integration time, and we only have 1 year here. And this, you have LASSO sensitivity after 1 year of integration time. So you can see here that LASSO doesn't have a kind of monotonic, or it's not really monotonic, but continuous curve like the other experiments. It has this curve here, and then you have an inflection and another curve. And this is because LASSO operates the core and the outer array as independent detectors. And what we learned to our surprise is that simply by operating the full array of SWGO as a single detector, we gain potentially a sensitivity in this hotspot where you have tens of TeVs of energy and you are seeing the bulk of galactic sources and doing galactic astrophysics. We can have a sensitivity almost 10 times that of LASSO in that region if we perform as expected. So it's again that we did not expect before, simply because we trigger and reconstruct all showers with all the detector, not separating for large and small showers. And so you can see here, SWGO will have a first phase. It's very difficult to build an experiment like this in one phase because of the cost. So it will be built in 2 phases. The first one is we are calling SWGO-A, and it's going to be basically a Hawk-size instrument installed at the center of the array. We are requesting NSF funds at the moment for this, which is a difficult time to request NSF funding, but it's the time that we have. And so you can see the performance of this Hawk-like instrument. And because of developments in electronics and in capacity and computation, you can see that an instrument that is even smaller than Hawk today can perform with a sensitivity that is a few times that of Hawk. So when SWJO is fully complete, because of these developments that I talked to you about, we expect to operate a factor of 10 in sensitivity from LASSO, which would be excellent, no? If we manage. So it would be really a transformational experiment. So this SWJOA is more or less only 400 tanks, and this is with the 2,000 core tanks. And then, of course, in Brazil, we are attempting to contribute with the outer array part, and we are looking for money to build 1,000 outer array tanks, which would provide this extension here to the ultra-high energies in the SWJOA context. But then, with something like 1,600 outer array tanks, which would be close to the final configuration, this is what you would have. So we would match the LASSO capabilities at the extreme energies for the Pevatron searches. And this is the other extremely important thing that SWJO will have. Nowadays, we detect Pevatrons, we detect these sources, but with a very poor angular resolution, because that's the limitation of the kilometer square array of LASSO, so which goes at the highest energies to something like 0.3 degrees angular resolution. By triggering and reconstructing the showers with both the outer array and the very dense core, SWJO should be able to push its angular resolution to something between 0.1 and 0.2 degrees. Now, this is very important because it starts to match at the extreme energies the angular resolution of CTA at lower energies. So we can then trace back the morphology of the sources from the extreme energies up to CTA energies, and then you connect that directly with the morphology in X-rays and lower energies. So you really have a continuous view of the source across the electromagnetic spectrum in terms of morphology, which is what you need to model particle propagation, how the source is behaving, etc., etc. So this is extremely important. So here is the angular resolution of the current IACTs. No? So we get close. And it is pretty much as close as one can get when you consider shower stochasticity in the shower development. And so just what I said, you see, so this is the map of the sky seen by Hess, and this is the map of the sky seen by Hawk. If you look at the first moment, you say, they have nothing to do with each other. No, they are the same thing. But you have to degrade the angular resolution of Hess to that of Hawk, and they match. So what we are trying to do with this new instrument is to bring a little bit the angular resolution of SWJO or of Hawk closer to that of Hess. So what Hawk sees like this, SWJO would be able to see like this. And this is the sky map as SWJO would see, and this is the region close to the galactic, a section of the inner galactic plane that you see here. So this is the Hess sky map, and you know how Hess is a leading instrument in the field and very important for astrophysics in the high energies, and this would be the sky map of SWJO. So you can see the resemblance of the sources is very close. Also, for multi-messenger, SWJO is going to be extremely important, because basically what it's going to do by having a large field of view and being able to see transients serendipitously is to get this uncertainty in the location of gravitational waves or neutrinos, if they have an electromagnetic counterpart, of course, and immediately reduce this localization uncertainty to several degrees to something that is a fraction of a degree. So for follow-up, this could be transformational. So if we are able to perform at the transient level with good sensitivity, then we would be a very powerful intermediary in the trigger sequence of multi-messenger astronomy. Just to conclude, I don't want to spend too much time with this. So we had candidate sites in 3 countries, Chile, Argentina, Peru, and in a range of elevations and latitudes that we're considering useful for us. In the beginning, so LASSO published its first results in 2021. So in the beginning, we were looking for a site that would be 300,000 square meters in size. After the LASSO results, we said, well, if we do that, then we are already outdated before starting, so we had to go to 1 kilometer square. So we changed our design in the middle of the way. Of course, water is the big difficulty that we have. Water at 5 kilometers above sea level is not common anywhere in the world. And these places are usually desertic as well, so you have other questions to consider when putting something like, now I forgot the number, but we are talking about 10 to the 5 cubic meters of water, perhaps, something like this. So we had to wait until 2022 to visit the sites, and that's what we did in October, November. For me, it was a horrible time because my daughter was 3 weeks old, but I had to go. So, but it was a very interesting visit. So we visit all the sites. We sub-selected those that were the best, so you can see. These are the worst for water. Well, all sites had to provide us with a solution for accessing the water somehow. Yes, at a certain reasonable cost and logistical, we had to be able to access water somehow. No? And all of them responded to this. But you see, the most important thing is that they are flat. Because if you have to do flattening of a 1 kilometer square, then you spend a fortune, even only to start. No? So they have to be sites where you go there, you put the tanks, and you go away. You don't have to bother too much with anything else. So there were 3 great sites in each of the countries, which was an important thing. But we were also paying attention at so we made a cost model for the construction of the observatory at each site. How much it costs to get the water, what's the kind of, how much taxes you pay, what's the cost of energy. So we did a complete cost table for all the sites of the detector, so we could compare the performance with the real-world stuff that would limit us. And the risks of operating each of these places, environmental impact is something that if you don't pay attention, the agencies kill you immediately. It's the first thing that they ask. Then they ask about the science, no? But this nowadays, it kills you. And also social impact. We have seen large telescopes, being scrapped because of local people resisting to that, and there is no way around. So this was an important part, and we believe that engagement with local community is important because we are going to their place. So we have to be wanted as well. We cannot force ourselves into any region. So we had our meeting in Rio at CBPF to decide where would be the site of the observatory. This points to the centrality of the South American participation in the experiment. Usually these things are decided in some institutions in Europe or the US, but the site was decided here. So here you can see the collaboration. So of course, we all know the result. Claudio was the big winner. He managed to convince us that the observatory should go to Chile. Well, at the time he thought it was a prize, now. And so it's going to be located at that Atacama Astronomical Park in an excellent site called Pampa La Bola. So this is the collaboration, or an important fraction of the collaboration, visiting the site earlier this year. So you can see how nice it is. It's a very vast plateau. It could be several kilometers square. So here you have the ALMA Observatory. We are basically at the same level. There are some other observatories in even higher mountains here, but the baseline here is 4.5 kilometers in altitude. We are here. This is basically a few kilometers from the border with Bolivia, and in this region, which is the Atacama Astronomical Park, that's a concession for astronomy around the ALMA Observatory. It's excellent because there is an excellent road that can take you there. It's the international road from Chile to Argentina in this part of in the north. We are just 40 minutes from San Pedro de Atacama, which is a place where everybody wants to go. It's a very nice place, so it's not difficult to convince someone to visit the site. And we have an airport 2 hours from us, which is very important. And a port, the port of Antofagasta, which I guess is the main port in Chile, 4 hours from the observatory. So here you can see the site and the road that takes to San Pedro de Atacama. It's really amazing. This is 2.5 kilometers in altitude, and then in 40 minutes you are at 5 kilometers in altitude. So SWGOA, which is the first phase for which we asked funding from NSF, around 20 million. And because you have to spend a lot of money to prepare the site, to bring an energy solution, to bring the water solution. So there is initial costs that are high, but it's going to be something like this, so something around 400 tanks or a bit less in this configuration. This is optimal for cabling length and things like this, cabling is very expensive always, and logistics of the operation, trigger geometries and things like this. The idea, so there's going to be made of these tanks, and here you can see some simulations of them, and a system of 2 PMTs in the middle observing the upper chamber and the lower chamber. The outer array, so this is something that we are also discussing, would have a configuration more or less like this. Interesting enough, the only thing that SWGO has already financed is the radio component, which is an extension of SWGO, but one of our collaborators got an ERC to put radio antennas for the observations of showers in the observatory. So now his biggest liability is the collaboration, which doesn't have the money to start the observatory yet, but he has the money to do the array. This would be built with our tanks, with these PMT modules adapted from KM3net that were developed in Naples, and it would be a sparse cluster of detectors in the outer region. And the idea is that we start building something like 1,000 tanks, and then get a second round of funds, or perhaps international funds, to complete it. These 1,000 tanks would cost around $6 million, which is what we are trying to achieve in Brazil. And then the detectors, photosensors, electronics would be an equivalent amount. The Pathfinder is going to be basically a little region where you install a few tanks and you test that everything works and that logistics works, bureaucracy works, your legal entity is doing the job it should do, and things like this. You can transfer money. I mean, all the things that you need to operate a large observatory. And we plan to do that between this and next year, or at least to break ground this year, to operate this next year, so that we have everything ready for when money comes. And this is just a video to conclude of a rendering of what would be SWGO when ready. This is what you're going to see is the real Google Earth location, so taken. So it's exactly the landscape as it is there. It's preliminary in the sense that there are things to still develop, but I think you are the first audience that is seeing it. It was made for the NSF application by the Mexicans. You see, you have all these catchy phrases and. So this would be the initial configuration, and then when we get lots of money, it explodes, and it looks very nice. You can see the road very nearby. Then you can see the tanks, and how they look inside. Empty. Just water and a photosensor. And then you have a car for comparison, and basically that's it. So it will become a touristic attraction when it's built, Claudio. So, and so I'll leave you with the summary. I think it's enough. Thank you.
Thank you very much for this talk. It's somehow interesting that last week we had the talk about the scary part of machine learning. Here we are seeing instead the nice part of machine learning that can make everything cheaper,
yes,
by improving our capabilities. So time for questions.
So thank you very much for your beautiful presentation. I was wondering if is there any indication of those data that you show to us of new physics, like in particle physics and so on?
If there is already any indication?
Yeah.
No. No, I mean, what we do in the various fronts of beyond standard model physics that we can probe or dark matter is always being put in more stringent limits, no, on many of these models, so kind of restricting the parameter space of the theory. But either in Lorentz invariance violation searches or axion searches or search for dark matter signals, no, there has been no discovery breakthrough. No, but this is an important part of the parameter space that we can probe. As was shown in the beginning of the school, some of this parameter space can only be probed by gamma ray experiments like us. So it's a unique part of the parameter space. And of course, constraining it as most as we can helps the theory to drive its efforts and to guide the future experiments that are going to look for this, either from direct detections on Earth or from other indirect detection methods.
Yeah, I was wondering because of the scale, energy scale that you put, you like...
The what?
Energy
the
scale.
energy scale, yes.
And the standard model works on the tera-electron volts, and I don't know.
You are talking about particle physics of the shower.
Yeah.
Oh, we see some things in the showers, for example, an excess of muons in the showers from what we would expected, from the extrapolations of LHC cross-sections and data, that, yes, poses questions on particle physics models as well on the shower development. Yes, so in this front, there are many interesting results that are being investigated because we are, in fact, dealing with processes that cannot be probed, interactions that cannot be probed in the laboratory. Yes, I had understood your question differently initially. But yes, this is, we have some signals that have to be understood.
Thank you for the presentation. I would like to ask a little bit about the exposure of the observatory to the celestial sky. So I think it was in slide 12. So,
yes.
Yes. So it's a little bit strange to me because it's like it has a zero exposure inside this circle.
Oh, this is because this is the celestial south pole. We cannot see it.
Ah, okay.
We are relatively close to the equator.
Oh, so you don't know the minimum and the maximum declination that the observatory will be able to see?
Yes, yes. So we are going to operate from plus to minus 60 degrees from zenith. So that's how this map is made. So it's too inclined for us to observe, for example, the South Pole, South Celestial Pole. It's 23. 23. It's like here.
Can you show, again, the countries involved in this?
Sorry?
What are the countries that are involved in this? Can you show again? I think it was one of your first slides, but I just went.
This?
No, the countries that are involved.
Ah, the countries.
Yeah.
Yes. So this.
And the NSF, what are the universities that are involved from the U.S.?
So the PI university is Michigan Tech, but there is a strong involvement from Los Alamos, a strong involvement from Maryland. Yes, these are the three main. There is University of Alabama. There is quite a few universities, but the main ones are these: Maryland, Michigan Tech, and Los Alamos Lab. And Utah, which is Wayne Springer. Yes, yes, Utah as well. Mike Duvernoy is in Wisconsin, where there is IceCube as well. Yes, so there is, but the largest groups, yes.
More questions?
So, Ulisses, I was wondering about the radio antennas,
yes.
because we discussed this before.
Yes.
So, in the map that you shown, I think it is slide 44, 43,
yes.
maybe?
That's a slide by Harm.
Ah, okay.
Yes.
Yeah, so I was wondering why the decision to not combine the water terrain cloud detectors with the antennas in the same spot?
Good question.
Yeah. And
this would provide a solution for power and things like this, yes.
Okay.
I think that since this is very preliminary, it's just an option of non-commitment to have a solution for the acquisition system of the tank that is compatible with the antenna. And I think that perhaps, but I'm not sure, people might be concerned with interference of the electronics.
Yeah.
But I don't know the experience of Auger, what it tells us.
And just follow up, do you know, well, this is probably very recent, but do you know if these radio antennas, they would be triggered by the WCDs?
This is also something to be defined. They could work standalone.
Yeah, that's what I was wondering.
But I imagine you can gain a lot by doing the trigger together, which could be an advantage, for example, from only radio experiments, yes? Yeah. But again, this is really early days for this. The project is made to do the reconstruction with the two data sets. But the trigger is something that has to be modeled. And this is simply because we don't have a final triggering model for the tanks anyway. So.
Yes. I have a question about the sky resolution, the sky localization resolution.
The sky localization resolution, you mean not the angular resolution, but the precision in which we can...
Angular resolution.
Angular resolution is, the best energy is 0.1, 0.2 degrees.
And then it scales down like...
Then it degrades up to, when you are at below 1 TeV, you basically have a degree or more.
Half of the sky.
No, degree or more. It's,
Okay.
it's always of the order of degree, even in the worst case.
Okay.
Yes.
Other questions?
I forgot that in your field, the degradation of angular resolution is obscene.
Yeah.
For sure. There comes Lasso. Yes.
Nice talk.
Thank
So for the tank, you are plan to using the pure water or ultra pure water?
Pure water or?
Purified water.
Purified water, yes.
Yeah. But you don't sensing the cycle of water. I mean the over time, the pure water may be getting worse.
So we want to get water to the level of purity like they have in Auger.
Like OJ. Okay.
So that you don't have to touch it. So you put there once, and you don't touch it anymore.
Anymore, okay.
And if you're brave enough, you can drink it after 20 years.
Okay, good.
Will you do?
Why not?
Okay.
In 20 years from now, I mean.
Why not?
I can promise things 20 years from now easily.
More questions? Yes, we have? No? Okay, so, yeah, we have over there.
Well, it's not more technique. My ask. I want to know about the last techniques that you using to reconstruct energy or core location, maybe.
The techniques that we use to reconstruct core location. So there are two main aspects that come into the, let's say, the first approximation of the core location. First thing is the core is where you have most of the energy of the shower deposited. So if the shower falls within the detector, you can use the distribution of energy in the tank, so the calorimetric measure of the tanks, to understand where the core is. And then you have the timing of the shower front. So we register with precision of a few nanoseconds the arrival time of the showers at each tank. No, and that's why we have the PMTs pointing upwards, because the particles enter and we get the Cherenkov light immediately. So with 1 nanosecond delay of crossing the tank. And from that, you have the time of arrival of the particles at each tank, and you build a model of the shower front propagation. And with that as well, you reconstruct not only the direction of arrival, but also the core position in the ground. So these two things. So the most critical thing for angular resolution in these experiments is the electronics, the temporal resolution of the electronics.
Okay. What about the reconstruction of energy?
Hmm?
Of energy, the reconstruction of energy that I remember that that you are using machine learning techniques to reconstruct the energy.
Oh,
of the
yes.
showers.
There are very sophisticated machine learning techniques. These are multi-parametric models that take in a lot of information, and sometimes it's very difficult to understand what is the parameter that is driving the resolution or the identification of the core and things, or the separation. So these are very large multiparametric models. So we don't understand all of them so clearly as you understand these simple analytical solutions that are the first approximations.
Okay.
Other questions? Okay, perhaps I can ask a very, I mean, I'm not from the field in any sense, so could be super silly, but I see that in this and in many other experiments, somehow you do simulations and then you build based on that simulation, or
Yes.
based on what you expect to see and so on.
Exactly.
Do you need to make a sort of balance? Because I guess if you constrain too much and if you rely too much on what you expect to see, then you could miss something that is unexpected. So do you need to make a balance between, let's say, what you expect and what you would like to see, but you're not sure?
So in our case, we had such a broad range of science questions that once we drove our design by the necessity of answering some of these questions, basically, we understood that we were covering a large discovery parameter space as well.
I see.
So, but of course, I mean, all these experiments, they are made to last 20 years. So I would be very surprised if, for 20 or 30 years, if 20 years from now, there is not an electronics upgrade, there is not a photosensor upgrade, something that expands this parameter space. But I think we are well covered. And of course, we had LASSO as a benchmark as well. No, as long as we are performing at least as well as LASSO, LASSO is really making steps in all fronts. So it was a great benchmark. You created a lot of trouble to us, yes. But we were so happy when your results came, because then we said, so now everybody wants to fund this because it's great.
If there are more questions, okay. If not, we can thank our speaker again.